Hi everyone. So in the last video, we introduced the definition of a tree and showed that every tree with more than one vertex has to have a leaf. That is a vertex of degree 1. In this video, I'm going to show that any tree on n vertices has n-1 edges. And this sort of numerical kind of characterization of a tree, that you can tell a tree just by counting the number of edges, as long as it's connected, turns out to be really, really important and have a lot of far-reaching applications. We'll see that the theorem that we showed before, that every tree has a leaf, plays a really, really important role when we think about trees, because it allows us to do induction on the number of vertices. And we'll see that in this proof. So let's get started. Okay, so we'll use induction on the number of vertices. And we're going to start when n equals 1. So when n equals 1, we have 0 edges. And our base case holds because 0 is 1 less than 1. Our base case holds. Okay, for the induction step, what do we need to show? So now we need to show that if for some n greater than or equal to 1, we know that all trees with n vertices have n-1 edges, then all trees with n+1 vertices have n edges. Okay, so if we need to show that if we know, that looks like some, if for some n greater than or equal to 1, we know that all trees with n vertices have n-1 edges, we need to show that this also holds for trees with n+1 vertices. Okay, so what we're going to do, and this is really important, it's really important that we focus on the conclusion of this if-then statement and take a tree with n+1 vertices, an arbitrary tree with n+1 vertices, and then show that that tree, about which we know nothing except that it's a tree and it has n+1 vertices, must have n edges. Okay, there's this instinct to try to take a tree with n edges and try to add a vertex someplace. But the thing is, if I have my favorite weird tree with n+1 vertices, how do you know that you're going to be able to construct my tree from yours? You really have to, in graph theory, start with the graph, in this case it's a tree, of the size you're interested in now, and then figure out a way to remove something in a very controlled way to see your induction hypothesis again. Okay, so let's let T be a tree with n+1 vertices, because that's what we want to know about. Then by the previous theorem, T has a leaf, V. Okay, so this is a vertex of degree 1. And now I want to define a new tree. Let T prime be a subgraph of T obtained by removing V and the one edge incident to it, obtained by removing V and the one edge incident to it, okay? And because we're removing a vertex of degree 1, we can really control what goes on when we do that, when we remove it. We know we're only removing one edge, and we kind of know, we'll know some things that have to be true about the rest of the graph. So maybe I'll draw a little example. This is like an example that's kind of in parentheses, okay, to give some intuition. So like suppose your original tree might look something like this. So I don't know, like this. Okay, now here is your vertex V that happens to be a leaf. There are many leaves, but this is one of them. And what we're going to do is we're going to let T prime be this part of the graph, okay? Now, what can we see must be going on? So I'm gonna say it and then I'll write it. First, when I remove that vertex V, I can't possibly disconnect the rest of my graph, right? Because if I take any two vertices, U and W, that are in the remaining graph, T prime, well, in the original graph T, there was a walk from U to, there was a path from U to W, okay? Or there was a walk from U to W. And if that walk used the vertex V, basically I would have had to take this edge here, walk out to V and walk back. So why do that? Any walk that goes from U to W, since I would have had to backtrack over that edge that went to V, just don't use it, okay? So I can't disconnect my graph. And also, T prime is a subgraph of T. Since T didn't have any circuits, I can't create circuits by removing edges, right? If T prime had a circuit, that circuit would still exist in T. So T prime must be a tree. Okay, so let me write that down. So let's show that T prime is a tree. And we can see, since we removed one vertex, it would have n vertices. To see that T prime is connected, let U and W be any vertices that are in T prime. There is a walk from U to W in the original tree T, because T is connected, okay? All graphs, because T is connected, all graphs are connected, that's part of the definition. And then if we had been silly enough to, ooh, that's weird. If we had used the edge that's incident to V, we would just go directly back. We would have to backtrack over it. So just don't use it. So we didn't need it. We didn't need it on our walk. Okay, so we still have a walk from U to W in T prime. Therefore, there is a walk from U to W in T prime. And then since T prime is a subgraph of T, since T prime is a subgraph of T, if it contained a circuit, so if it contained a circuit, then that circuit would be in T as well, which would be a contradiction. Therefore, T prime is a tree, and it's a tree with only n vertices. So by our induction hypothesis, so we know how many edges it has by our induction hypothesis. T prime has n minus 1 edges. And then we realize, well, what's the difference between the number of edges in T prime and the number of edges in T? Well, because we removed a vertex of degree 1, it was a leaf. When we removed it, we only took off one edge. And so when we put it back, we have n edges. Okay, we removed only one edge when we created T prime. Oops. So T has T has n minus 1, the number of edges in T prime, plus 1, which is n edges. And that's exactly what we wanted to show. All right, that is enough for this video.